All right, so high and low pass for 300. It's not resonance, it's a low pass filter, low pass filter. Sometimes that may not be stated. It may just say something like, it will say, if it uses the word cutoff frequency, then that would tell us that we are looking for a filter of either high or low pass, and it's up to you to determine it. But in this case, we know that we're looking for an RC low pass filter. And in this class, that's what I said they would always have is RC. And what it wants to know is we have an R, right, of 5 ohms. And we're going to design an RC low pass filter, which will look eventually like this. Here's a resistor and here's a capacitor. And I said it's almost worth memorizing that this is what a low pass filter looks like. But remember that at very low frequencies, this capacitor will turn into a short. So the filter that we are designing already we know has 5 ohms. But what we don't know is we're going to have to solve for a C of something in farads because we're designing this filter. And what are we trying to design it for? It says 3 to 30 megahertz. And so the low pass side of it is that everything below 30 is what we want, right? We desire frequencies below 30 megahertz. So to do the full filter, if we were going to allow 3 to go through, we would also need a high pass filter, allowing things above 3 to be plugged into the circuit as well. But for just this part, we're designing the low pass portion, which is 30 megahertz. So this is the desired frequency below. So this is essentially our cutoff frequency. Everything below 30 megahertz is what we want to allow to pass through. So we use FC equals 1 over 2 pi RC, which in this case, we'll rearrange it to where we're solving for C because we're designing this filter. So 1 over 2 pi R FC, FC being the cutoff frequency. And C is 1 over 2 pi, 5 ohms, 30, and I'll write E6 because that is mega. So just as a reminder in your calculator, that's how you need to write it in. 30 E6, E being the times 10 to the, and C equals 1.06 nanofarads. So right here, 1.06 nanofarads. So if I was boxing my final answer, I have designed or I drew the circuit and labeled the frequency response curve as the next step. But I did draw the circuit, check. Frequency response curve means as a function of F, what happens to my V? There's 2 ways you can write it. You could write AV, right? AV being V out over V in, or you could also, you could also make it as a function of, and just say, what is my V out? Well, that, and right here is my cutoff frequency that I want everything below that to let the voltage pass through or let the current pass through, which means it has a high output voltage. And right there would be 0.707 V initial and V initial. So at a very low frequency, all of the current gets to go through, all of the voltage remains there. The voltage across it remains the same. But at the cutoff frequency, 0.707, right? And that is because we would eventually, that 0.707 generates from that AV equation, and that R and C aren't equal, but R and XC are equal. So what we're left is 1 over the square root of 1 over 1 squared plus 1, which is 1 over the square root of 2, which is 0.707. That's just the extra explanation for where the cutoff frequency is coming from. It's when the reactance of that capacitor equals the resistance. But in this case, right here is all I would need if I was asked to draw that response curve like that.